I will be giving an introduction to equilibrium in this video. A big idea behind equilibrium is that reactions can go backwards. Take a look at this reaction. I represent all my reactants using the letter A and all my products using the letter B. The double-sided arrow here represents that the reaction is reversible. In other words, B can turn back into A. We can separate this into two reactions, the forward reaction and the reverse reaction. Let's take a look at what happens in this reversible reaction. In the beginning of the reaction, we have only reactants, so we have only A. As time passes, we consume A to produce B. As we consume more and more A, the rate at which our forward reaction can proceed will start to slow down. Now, once we start producing B, our reverse reaction becomes possible. As we produce more and more B, the rate at which our reverse reaction can proceed will start to speed up. But we don't slow down our forward reaction forever, nor do we speed up our reverse reaction forever. The speed of our forward reaction and reverse reaction eventually level off at the same rate. Think about it. If I want my reverse reaction to go even faster, I need more B. At this point, I can't have more B because it is being consumed at the same rate that it is being produced. Same thing with my forward reaction. If I want my forward reaction to go even slower, I need less A. At this point, I can't have less A because it is being produced at the same rate that it is being consumed. This point is called equilibrium. To restate, equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction. A common misconception is that equilibrium means that the concentrations or amounts of reactants and products are equal. This is not true. Again, it's only the reaction rates that are equal. However, you should note that concentration will not change at equilibrium, as shown by the constant lines. When dealing with equilibrium, you will commonly see a K with a C subscript. This K represents the equilibrium constant, which is the concentrations of substances at equilibrium. These brackets represent concentration, which is also known as molarity. These little letters represent coefficients of our substances. Take a while to see how this reaction corresponds to the equilibrium constant expression. As an example, I'll write down the equilibrium expression for this reaction. Now, we don't have an exact number because we don't know the exact concentrations of our substances, but you'll often be asked to write down the expression before finding the actual number. Something very important to keep in mind is that you never put solids or liquids in an equilibrium expression. Always ignore them. The reason so is because we're analyzing concentration changes with the equilibrium constant. Solids and liquids have constant concentrations, so they are left out of the equilibrium expression. When finding Kc, only put aqueous solutions and gases in the equilibrium expression. Take a look at this reaction. Using the information I have just given you, pause the video and try to write down its equilibrium expression. Pay attention to the states of matters of the reactants and products. Notice that I left H2O out of the expression. Again, always leave solids or liquids out. Something I wanted to mention is that you may see K with a P subscript instead of C. The P represents pressure. Its equation is similar to that of a Kc equation. If you're doing a problem and you're asked to give the equilibrium expression in terms of pressure, you must use this equation instead of this one. The rules for Kp are similar to Kc, but you can only include gases in the Kp expression because partial pressure applies to just gases. So leave out liquids, solids, and aqueous solutions for Kp. Also, you cannot use brackets, you must use parentheses instead. One last thing to note is that you must write your molecules as a subscript to pressure. This may be a lot to take in, so I'll demonstrate an example. I'll write the Kp expression for the same reaction. Notice how it's different from the Kc, since we excluded the aqueous solution, put parentheses instead of brackets, and put CO2 as a subscript to pressure. So I have changed the reaction a bit. I want you to try and write the Kp expression for this one on your own. Pause and try. Hopefully you got it correct. It is very important to not confuse Kc and Kp, since you will lose points in an AP exam if you do. The problem usually indicates which one it wants by mentioning either concentration or pressure. Hopefully you have some idea on how to write equilibrium expressions now. I'm going to talk more about what the equilibrium constant actually means. This is the equilibrium constant, as I have mentioned earlier. It has no units. It represents the concentration of your substances at equilibrium. It's only valid for a certain temperature, meaning if you change the temperature of a reaction, you're going to change the K value as well. The reason so is because reactions are either exothermic or endothermic. This means that changing temperature will change the amount of reactants consumed and products produced. If the amount of products or reactants change, then, according to this equation, so will our equilibrium constant. Moving on. The big idea is that if you have a value that is much bigger than 1, then, according to this equation, your concentration of products is much higher than your concentration of reactants. If you have a value that is much less than 1, then, according to this equation, your concentration of reactants is much higher than your concentration of products. So a reaction that goes almost to completion will have a very high K value, since most of its reactants turn into products. On the other hand, a reaction that is very unreactive will have a low K value, since most of its reactants don't turn into products. From time to time, you're going to be asked about what happens to a K value of a reaction when it undergoes a certain change. You should note that reversing a reaction will cause the K value to change by the reciprocal of the original K value. The K value here is 100,000, but when we reverse the reaction, it becomes 1 over 100,000. Additionally, if you change the reaction by a certain factor, the K value will change to the power of that factor. When I double everything in this reaction, my K value changes by the power of that factor, so my K value is squared. If I tripled everything, then my K value would be cubed, and so on. The last change I'll talk about is adding reactions. If you combine two reactions together, then you will multiply their K values to get the K value of the new reaction. This idea is similar to Hess's law since you're reversing reactions or manipulating them to change some outcome value. So those three manipulations are ways of quickly finding the new K value of a reaction when it undergoes one of those changes. I'll talk about more complicated changes in another video. I'm going to throw one more practice problem. Try to apply some of your knowledge by answering this question. Refer to this equation for help. Pause and take some time to answer. Good luck. So here's the answer. Hopefully you got it right. That's all for today. I'll make more videos on equilibrium soon. Thanks for sticking with me. Goodbye.